In this lesson, we're going to be talking about measures of variation. Now, hopefully, by this time, you've already done central tendency, which is the measure of the center of a data set, which is, of course, very important. But equally important is how is that data distributed around the center? Is the data very close to that center mark, or is it spread out far away from the center mark? And that's what measures of variation try to answer. We're going to be talking about several different ones. We're going to talk about mean deviation. Now, mean deviation is not widely used, to be honest, but it's actually a really good conceptual basis for standard deviation. A lot of people will get kind of confused, but if you understand the concept of what standard or mean deviation is, I think it'll be very helpful. We have standard deviation and sample standard deviation. These are, in fact, incredibly important. They are used all over the place when we're going to be talking about probability and confidence intervals and hypothesis testing. We are constantly going to be using standard and sample standard deviation. So it's super important that you get a real good basis and grounding in these measures. As part of standard and sample standard deviation, we'll also be talking about variance, which is a portion of those. Now, what we're going to be doing is using an example. So here we have a data set. We might say this is a flower grower, and he has 15 different rose plants. Each one has different number of rose blossoms on it, and he counts them. And so one rose bush has 23 roses on it, while another one has 5, another one 5, 13, 14, and he has his 15 rose bushes that he has in his farm. So the first thing to do is we want to find where is the middle of this data set, and we want to get a sense of how things are distributed even before we try to measure that sense of distribution. I'm going to do a few things to help myself. One is I'm going to sort in ascending order this data, and I'm going to draw a histogram of this data, and that will give me a good visual on how the data is distributed. Now, here's the data sorted in ascending order. So you can already kind of get a sense of where the center is likely to be. It's probably going to be in this area. Now, what I've also done is I've entered this into my calculator. Here's the original data in L1. I'm going to use the calculator to create a histogram. So I'm going to go to stat plot, go into my first stat plot. Make sure it's on. I've chosen histogram. So it's set on L1, which is good. Now, what's going to be very important is the window settings. Now, having been the one to generate this data, I know that what the intervals are going to be to show this well. And I think if we do this maximum up to 30, and the interval is going to be 6. We're going to have, it's going to be low frequencies. And let's see if that works. Let's look a little bit farther up. We'll maybe make that 35. And that looks nice. A real nice distribution. I can hit trace. And 4 to 10, 10 to 16, those intervals of 6. So I can come over here and I'll just make a quick sketch of that. So looks something like this. Nice and symmetric. And that's our basic data. Can put this in. All right, so we have, it goes up by 6. So that's going to be like that. So, so now we're actually going to start talking about how do we measure this degree of variation. Well, the first thing we're going to need to do is actually find where the center is. And for standard deviation, sample standard deviation, the center measure we're going to use is the mean. So we need to find the mean of this list. We can, of course, add them up, divide by 15. What I'm going to do is go and just use the mean function of L1. And here we know that the mean is 18.53. So there's our center. Now, what I'm going to do is get a new screen and start graphing or plotting these data points on a horizontal number line. So here's my number line, and I'm going to just plot my data points on this. So I have two number 5s. I have a 13 and a 14 and a 17 19 and 20 23 27 and 28 and 33. I'm going to put the numbers on those. So now what we want to do is mark where the center is, which is our 18.53, which is going to be somewhere around here. And I'm just going to do a big slice right here. 18.53, there's our mean. So when we start talking about variation and measures of variation, what we are going to try to measure is, well, how far away, on average, are all the data points? So what we can do is say, well, how far away is that one? And then how far away is that one? And you can see where this is going to go. There are all the deviations, right? How far each data point deviates from the mean, right? This will deviate a certain distance, this one will deviate a certain distance. But we don't care just about 1/2, we want the deviations for these as well. So there are all the deviations on the upper side. So we just need to calculate the length of these. Well, if we take this nice long one, we know that it's 18.53, this is at 5, so we're just going to subtract. All right, we have 18.53 minus 5, and that's going to give us that deviation of 13.53. All right, so this is 13.53. Now we're going to repeat that for all the other ones. And there they are. Now, what I want to draw your attention to right now, very important, is how we calculated this. We did the mean minus the data. So if we did this symbolically, the mean is x bar minus x. Right? And that's how we calculated all of these. Now, if we did the same thing over here, if we did the mean minus each data point, we'd do 18.53 minus 33 for this first one, and we'd end up with a negative number, negative 14.47. So we don't actually really want that to be negative. We don't really care whether it's on one side or the other, which is what a positive versus negative deviation might denote. We just want distance, the absolute value. So what we're going to do is switch it around and say, well, we want positive values, so we're going to take the data and minus the average. And that'll give us all positives on this upper side. This will now be positive 14.47. And we get all of these deviations for the data above the mean. So now we have all the individual deviations. We want to get a single measure of variation. So one approach is to say, well, why don't we just take the average of all these deviations? And that should give us a good sense of how far apart, on average, all the data is. So what I'm going to do is list off all the deviations, how far each data point has deviated, because we have to be a little bit careful. There isn't just one phi. There's not one deviation of 13.53. There are actually 2 5s, so there are 2 of those. And so if we're going to average them, we just need to make sure to accommodate every single data. So there are all of the individual deviations, and there should be 15 of them because there are 15 original data points. Now what we can do is say, all right, let's find the mean of these 15 deviations. And what I can do is I can put these into L2. And I can even show you how to do this on a calculator, which is kind of interesting. And pretty easy, actually. You go to L2, and if I want to find all the individual deviations, now I have to be a little bit careful here because I switched my formula here and here. It's hard to do that on a calculator. So in order to accommodate that and make sure we don't get any negatives, I'm going to go to Math and go to the Number menu, and ABS stands for Absolute Value. So I'm going to put in absolute value and then go my mean, which is 18.53, minus all of the data in L1. And there's our 13.53s. We can get all of those. Those are all of the individual deviations like they are over here. So now, what we can do is call back the last thing we did and change that to summing L2, or finding the mean of L2. And there's the mean. So we're doing the mean of L2, which is 5.89. I'm just going to use 2 decimal places. So on average, the data seems to deviate by about 5.98. What I can do is set up some boundaries and say, all right, well, let's go 5.89. Sorry, I think I said 9.8 earlier, and see where that gets us. And we can maybe do that to both sides because, again, we really didn't care whether it was above or below, so it could go to either side. So as you go above, you start at 18.53, add the 5.89, you'll arrive at this upper boundary of 24.42, which is, around here, we'll say. And then you drop down the same distance, 12.64, and that's going to be probably somewhere around here. So it gets this sort of middle zone, right, where the average of the data seems to fall. Now, because we did just a simple average, the mean, there's going to be about 50% of your data in here, depending a bit on how the data is distributed. But if it's a perfectly normal distribution, right, there should be about 50% in this range. So now what we're going to do is move on to standard deviation. So this measure right here is what's known as the mean deviation, because it's the simple mean of all the deviations. Right? And as I said before, this is the measure which really isn't used particularly. But I think it's much easier to understand what's going on with this one, because you just find your deviations, you're finding the average of them. About 50% of your data is going to be in this range, and so that's a really nice measure of dispersion and variation. You know, if this number is smaller, it means more of your data, or the middle 50% of your data, is tighter to the mean. If this number is bigger, it means it's more spread out. So it gives you a nice sense of distribution. So what we're going to do next is talk about standard deviation, which is a variation on this same theme. So here I'm starting back more or less at the beginning. I have my number line with my data points. I have my mean split in the middle. I've indicated all the deviations. But now when we talk about standard deviation, we're going to be calculating these deviations a little differently. And as we talked about a moment ago when we were dealing with the calculator and having to use that absolute value as a way of dealing with this issue of a positive and negative, doing it by hand, we just change the order. Well, it's hard to do that on the calculator, so we used absolute value, right, to do it this way. Well, there's another way of dealing with that whole negative number issue and making sure we don't have those negative numbers. And the other way of doing that is by taking the mean, subtracting the data, and squaring it. Right? That's the major difference between mean deviation and standard deviation, is now we're squaring it because, of course, a negative squared, it becomes a positive. So if you square something, you're guaranteeing that it will always be positive. So if we were to get these deviations and square them, they become this. You'll notice that these numbers are, of course, much larger than the other numbers. This is 183.06 versus 13.53. Right? Because if you square 13.53, you get 183.06. So these are going to be much larger. So if we list the squared deviations, it's going to look like this. And again, there should be 15 of them because there are 15 data points. Each data point has its own deviation. So now, if we take the mean of this, I'm going to actually do this kind of out in more detail. So if we, and it's going to be easier to do this in the calculator, and I can show you how to do that. So first of all, here are the individual deviations. If we want the square of these, well, all we have to do is go L2 squared, right, in L2, and it's simply going to square all of them. And there's our 183.06, 19.91. So those are all the squared ones in L2. So now what I'm going to do is go to my list. And in math, number 5 is the sum function. So I'm just going to sum L2. So we have the sum of L2, I'll say that this is an L2, is equal to 863.73. And this is going to be important to show this detail. This is where we're getting into the difference between standard deviation and sample standard deviation. Because if we want to now average all 15 of these, right, we would, the mean would be the sum of all of them divided by the number of them, which is 15. Right, and if we do that out, we get 57.58. Now this has a particular name to it. We talked about, or I mentioned this earlier, this is your variance. Right, whenever you have essentially the average of the squared deviations, this is called your variance. You'll notice 57.58 is a pretty huge number in comparison to the mean. I mean, if you remember what we did back on this previous page with mean deviation, we took our mean and then we added up 1 and down 1, and that got us about 50% of our data. Well, if we add, and we were only adding 5.89. If we take 18.53 and add 57, we're blowing right past both the maximum and minimum of our data. So it's going to have 100% of our data. Something's wrong, right? And what's wrong is the fact that we squared, all these deviations. So these aren't the actual distances. They're much bigger than the actual distances. They're the squared value of them. So if we want to bring this back down to a reasonable and sort of normal level of this data, what we need to do, and this is going to be the standard deviation, is square root this number. And that's going to be 7.59. And that's the standard deviation. Now you'll notice that 7.59 is different than our mean deviation of 5.89. Well, as it turns out, this 5.89 was 50%. Standard deviation actually is going to capture approximately 68% of the data, not 50%. And the interesting thing is, why is there the difference? It seems like when we square root, we're just undoing what we did before. Shouldn't we get the same answer? Well, yes, the 863.73 is squared, and we're square rooting it, but the 15 isn't squared. And yet, we're still square rooting it in a sense because it's part of this 57. So that creates a slight difference. And the standard deviation is always going to be bigger than the mean deviation. It's, again, going to be about 68%. One of the reasons I think standard deviation became relatively popular and is the standard measure that's used is that 68% is a more conservative value. If you were a manufacturer and wanted to know if all of your product was being manufactured properly, then is it better to know 50% is within tolerance or 68% is within tolerance? Well, you want to know 68. It's more conservative value. So I think that's one of the reasons why it was widely adopted. Now, once we get into standard deviation, right, what we need to do is talk about what is the difference between this and sample standard deviation. To do that, I'm going to get a new page. So let's summarize here. Standard deviation, sometimes abbreviated like that, StdDev. If we want to write this as an equation, then of course we're going to be square rooting the whole thing. It's going to be the mean, so it's adding up all the deviations divided by the number of numbers. So number of numbers is usually n. And this is going to be the sum of all of the squared deviations. So first of all, we start with the capital sigma, which is the notation for summation. Right? The deviation is x bar minus x and squared. So that's what the equation looks like in its most condensed form. Now, variance is just the inside part. It's just the sum of the squared deviations over n. So the standard deviation is just the square root of variance. The variance is the square of the standard deviation. And that's all there is to that. Now, sample standard deviation. This gets into a kind of a tricky question of what is the difference between sample versus population. Now, when we talk about population, that's every individual of interest is known. And so, again, in this example question, if we were talking about rose bushes, and there's a particular farmer and he had 15 rose bushes, if he didn't care a lick about anyone else's rose bushes and we were just worried about this one farm, I suppose you could say that was the entire population of rose bushes of concern. But really, there are a lot of other rose bushes in the world. So it'd probably be a little bit more accurate to say, well, those 15, if we wanted to talk about what all of the rose bushes might be like, those 15 would really just be a sample, a portion of all of the rose bushes in the world, or of a particular species, or however you want to define it. So that's the difference between a sample, which is a portion, and a population, which is all the members are known. So if we were to think of these rose bushes as just a sample, and we wanted to calculate the standard deviation, there's a slight adjustment which gets done. Because if we took these 15 rose bushes as one sample, we get one standard deviation. If we went somewhere else and took a different 15 rose bushes, we'd get a slightly different standard deviation. And again, if we did it a third time in some other place, we'd get a third and slightly different standard deviation. There's variation between samples. And so if you're dealing with a sample, you're essentially a little less sure about your results. And so to adjust and accommodate for that, the averaging is adjusted. So you do the sum of the squared deviations, but instead of dividing by the number of numbers the way you normally would, you actually divide by one less. And this is going to make the standard deviation a little bit bigger. And that's, and I'm sorry, I'm going to have to make a correction here because, of course, we use a different symbol. All right, this is S. All right, so you can distinguish between sample standard deviation and regular population standard deviation. So this is going to make your sample standard deviation a little bit bigger than your standard or population standard deviation. Again, because you're just less sure. And so it's, again, a little bit more conservative. And so you can have a sample variance, which would be just the inside part as well. And those are your measures of dispersion or measures of variation. Just to compare, if you were to do the sample standard deviation on those rose bushes, you end up with 7.85. And let's maybe go back and look. In comparison, there's 7.59. So again, the sample standard deviation is a little bit bigger, a little bit more conservative. And if we go here and add our, I'm going to clear this a little bit so that we can see what I'm going to do next. Get rid of this too. So if we move our standard deviation above and our standard deviation below, oops, that's 5.9, then we arrive at 26.12 and 10.94, which is approximately here and approximately here. And again, this region now doesn't capture 50%, it captures about 68% of the data. And so we get the sense of how far is the middle 68% from the center. So, and of course, sample standard deviation would extend this out a little bit farther. In a lot of ways, it probably wouldn't go beyond the 27, so the percentage that it would capture really isn't that much difference in this case, but sometimes it can make some difference. So here is the summary page, and hopefully if you have any questions about standard or sample standard deviation, variance, hopefully this answered them.